Hi, I'm Anish, and this semester I worked with Arvind, George, Nathan, and Thomas, and we worked on developing models to predict the outcomes of NBA games. So, since the very beginning of basketball as a professional sport, there has always been an avid interest among fans and analysts to predict the outcome of games. In addition to doing this type of prediction for the love of the game, many people stand to gain financially from the outcome of games due to sports betting. Additionally, teams can use this type of data to better plan out their practices based on which games are most likely to win. So, our goal for this semester was to attempt to match or improve upon existing models whose accuracies hovered around 70 to 75%. And focusing in on the scope of the project, the problem we wanted to focus on was helping teams develop new metrics to determine which of their future matchups will be a tougher battle, allowing them to better allocate their time in preparation for the games that they have ahead of them. But first, we had to consider whether the project was even realistic in the first place, which relied mostly upon the availability of data. But because of the immense interest in basketball and analytics, we had plenty of data to go off of. And there were rich statistics available from each of the over 6,000 games. Which leads us into the data collection part of our project. So, our data came from a Kaggle dataset that contains stats for every game since the very first NBA season, which was in 1946. There's data on each of the 30 teams, 4,500 players, and even more than that. And the data is constantly being updated. From all that, we filtered the data down to 19 features that best represent an NBA game. That means we didn't really include information on players or teams, focusing completely on match-related statistics. We also decided to remove a lot of the earlier games from before 2002 because the game has changed significantly due to rule changes since then. And that leads us into the data pre-processing part of our project, which was pretty involved because the data was pretty messy when we got it. So the first thing we did was remove all of the duplicate games. Then we identified any game with incomplete data, such as games that had been accidentally logged while still in progress. We went through the short list of incomplete games one by one and either updated the data to be correct when possible or simply deleted that row. Some data had likely been pulled from a better source than others, and as such had more features associated. Unfortunately, the size of the dataset from that source would be smaller than what we would have liked, so we just had to disregard those features. So moving on to the actual features and data points, each individual data point was a game and its associated statistics. So the features that we had to use either had to be intrinsic to the game or calculated from the team's previous performance. So we chose our features such that for each game, all features are in the format of the home team's stat minus the away team's stat. And rather than using the actual statistic, we took the running average. And calculating that running average ended up being the most computationally intensive part of our pre-processing. So for an example of this feature formatting, feature FGM is the home team's average number of field goals minus the away team's average number of field goals. And we chose to format our data in this way as that's how it was provided in the dataset. And team differential is a common way to display basketball statistics. So, for example, that's how it's displayed in the spread of a game in sports betting. So moving on to the actual features we chose, we ended up selecting 19 from the vast amount of features from the original dataset. And we made that decision to choose those 19 features based on data completeness. So for example, some of the features were field goals made, 3-point field goals made, free throws attempted, and offensive rebounds. And there were 15 others. And lastly, the target variable that we chose for our models to predict was goal differential for each game, which is just the home team's points for that game minus the away team's points. And the last step in data pre-processing was feature reduction. So we ended up going with PCA for our feature reduction method. We tried several different levels of retained variance, but ended up going with 90% since that yielded the best results for the models we were training. This also reduced the number of features by about half, from 19 to only 10. So moving on to the actual models that we used, the first method that we tried was a form of unsupervised learning. We chose scikit-learn's k-means model and stored the data using pandas and numpy. We split our dataset into a training set and a testing set with an 80-20 split. For the k-means model, we chose two clusters with the idea that one cluster would be for the positive outcome differential, which means that the home team won, and a negative outcome differential, which means that the home team lost. And the average accuracy that we achieved over 10 runs without PCA was about 60.7%, and with PCA we achieved about 61.1%. which is a good sign because it indicates that not only did PCA reduce the number of features in our data, making training less computationally intensive, but also it slightly improved the accuracy of our model. However, 60 or 61% accuracy isn't nearly enough, which is why we decided to venture into supervised learning. So the second method that we tried was a decision tree model, which is a supervised learning model. So for this model, the data set was also split into a training test and a testing set with an 80-20 split. And in the implementation of the model, the maximum depth allowed for the decision tree is a significant factor in the overall accuracy of the model. And we tested a range of maximum depth values from 1 to 20 to determine which one produces the best result. And here's a graph showing some of the values of max depth that we tested for the decision tree. And as you can see, if we increase a max depth too much, the accuracy starts to deteriorate. And keeping the max depth between around 2 and 5 is ideal for this model. And for our third and final model, we used another supervised learning method, specifically a neural network. And just like the previous two methods, we used an 80-20 split with training and test data. And we used TensorFlow's sequential class to create our neural network, which was a 6-layer network using dense layers. And after messing around a little bit with some of the hyperparameters, we settled on training with a learning rate of 0.001 over 10 epochs. And we tested various activation functions and settled on leaky ReLU as that's what gave us the best performance. And as you can see here, we have a graph of accuracy and loss plotted against several different activation functions. And it's clear that leaky ReLU is significantly better than the others, as it achieves significantly higher accuracy and lower loss than some of the other activation functions. All right, so I think overall we got most of the results that we were expecting in terms of the unsupervised model performing worse than the supervised learning models. However, one thing that we were unable to achieve was an accuracy of around 0.72 to 0.75 or higher. However, we came pretty close with an accuracy of about 68%, which was using our neural network, using leaky ReLU as our activation function. And we suspect that this is because of the data that we chose to use. That is like the 19 features that we originally chose, which got reduced to 10 features through PCA. Maybe using a different data set would have yielded different results, maybe including more features from a cleaner data set or from a data set from a private company that might have collected more statistics could have yielded better results. But ultimately, 68% came pretty close to our target of around 72%. And we are interested to see how this model fares with the games in this upcoming season.